Yeah, welcome to the lecture on electrical circuit analysis. So, this lecture is on network theorems. So, in this lecture we are going to state the superposition theorem and Thevenin's theorem and how to solve the problems by using this superposition and Thevenin's theorem. That means, for the given network how to apply the superposition theorem and Thevenin's theorem. So, let us see one by one. So, the learning objective of this first lecture, that is today's lecture, is to state the superposition theorem and to solve the given network by using superposition theorem, and the next one is to state the Thevenin's theorem. That is, what is the statement of the Thevenin's theorem and what is the statement of the superposition theorem and how we have to apply this superposition and Thevenin's theorem for the given network problems. Okay. So, let us see one by one. Now, first one is the superposition theorem. So, this superposition theorem states that in any linear network the response in any element is equal to the algebraic sum of the responses, individual responses. That means, the response in the sense whether it is a voltage or current. So, according to the superposition theorem, the voltage across any element or the current through the any element in a linear circuit is the algebraic sum of the voltage across them or current through them, that elements, due to each independent source acting alone. So, this is the statement of the superposition theorem. So, to turn off these independent sources, so we have to kill the inactive sources. So, if it is independent voltage source, it is replaced by short circuit, that is 0 volts, and if it is a current source, so it may be replaced by a open circuit, that is 0 amperes. So, dependent sources are left intact. Dependent sources are intact, but independent source only we will kill them. So, that means so what are the steps to apply the superposition theorem? So, first step is so to turn off all the independent sources except one source. That means, so if there are two sources are acting in a network, so first we have to assume that only one source is acting at a time. The remaining sources must be killed. So, killing in the cells, so voltage source replaced by short circuit and current source replaced by open circuit. And the next step, so we have to kill the first source and the second source is acting alone. Now, we have to find out the response. Now, in the third step, we have to add the two individual responses, so which will give you the whole response of the network. So, that is the superposition theorem principles. So, that means find the output voltage or current due to that active source using nodal or mesh analysis or any network principles. Now, we have to repeat the first step for each of the other independent sources. Now, for next step is find the total contribution by adding the algebraically all the contributions due to this superposition theorem. Now, how to turn off independent sources? So, as we discussed, so the step one is we have taken one source. So, let us here taking one assumption. Let us be for the given network only two sources are there, two independent sources are available. So, first source is a voltage source and second source is a current source. Now, in the first step, so we have to assume that only voltage source is acting and we have to kill the current source, that is replaced with open circuit. And the next step, we have to kill the current source, we have to kill the voltage source and we have to act the only voltage source, current source. So, then you find the responses. So, add at the last step you add the responses. So, it will give you the total response. So, superposition involves more work, but simpler circuits, but this superposition is not applicable to the measurement of, that is calculation of power. So, this superposition theorem is only applicable for linear circuits only, it is not applicable for non-linear circuits. The circuit which consisting of a non-linear elements are calling as a non-linear circuits. So, the circuits which consisting of a linear element we will calling as a linear elements. So, what is a linear circuit? Linear element means the element for which the voltage versus current characteristics is a straight line passing through origin, then that element is called as a linear element. So, resistor, inductor, capacitor are the best example for the linear elements. So, this superposition theorem is applicable for only linear networks. So, to apply the superposition theorem, so let us take one example problem. The question is, by using the superposition theorem, we have to find out the voltage across the 4 ohm resistor. We have to find out the voltage across the 4 ohm resistor. Now tell me, here how many sources are there? 2 sources are there. One is voltage source having the voltage 6 volts and another one is the current source having the current of 3 amperes. Which means to apply the superposition theorem for the given network, there must be minimum 2 sources must be present. Minimum 2 sources must be present. So maximum any number of sources, but minimum 2 sources must be present to apply the superposition theorem. So here 2 sources are there for the given circuit, given network. So we can easily apply the superposition network to solve the voltage across these 4 ohm resistors. So let us see what are the steps to solve the given network by using the superposition theorem. So first step we are taking we assume that only 6 volt voltage source is acting, 6 volts voltage source is acting. Okay. So and we have to kill the current source, that is 3 ampere current source is killed here. So 3 ampere current source killed, so it is replaced by open circuit. So let us see in the network. Now since there are two sources, so the voltage across this 4 ohm resistor is V equal to V1 plus V2, where this V1 is nothing but the voltage across the 4 ohm resistor due to the 6 volt voltage source, and V2 is the voltage across the 4 ohm resistor due to the 3 amperes current source. So therefore, according to the superposition principle, the total voltage across this 4 ohm resistor is equal to the algebraic sum of this V1 plus V2. Okay. Therefore, now we have to find out the voltage across the 4 ohm resistor for the only when the 6 volt voltage source is acting for the first network. Now here this 6 volts 8 ohms, okay, 6 volts 8 ohms and 4 ohms are connected in series. Therefore, we can apply the voltage division principle to find out the voltage across the 4 ohm resistor. So what is the voltage division principle here? The voltage division principle is, okay, the voltage division principle is, okay, total voltage into, if you want to find voltage across any element in a series connected elements, the voltage across any series connected element is equal to the total voltage into, that is 6 volts into that resistance by, okay, 4 ohm by total resistance 4 plus 8. So 4 by 12, that is 1 by 3 and then to 6, so therefore 2 volts. So therefore, the voltage across this 4 ohm resistor due to the 6 volt voltage source is 2 volts. So let us, this is V1. Now how to find out the, now in the next step, okay, we have to find out the voltage across this 4 ohm resistor when only the 3 ampere current source is acting, that is second network. Okay. So we kill the voltage source, that is replaced with short circuit. See, the voltage source replaced with short circuit. Okay. So now we have to apply the, see, I want to find out the current in this because these all 3 8 ohms, 4 ohms and 3 ampere sources are connected in parallel. So I am using here current division principle to find out the current flowing in the 4 ohm resistor, that is I3. So therefore I3 is equal to, so according to the current division principle, so the current flowing in any parallel connected element is equal to the total current into, that is 3 amperes into opposite resistance, that is 8 ohms by total resistance 4 plus 8. So 4 plus 8 is how much? 12. So 8 by 12, that is 18, 23, 24 by 12, that is 2 amperes. Now what is the voltage across the capacitor? So according to the Ohm's law, so V2 is equal to, that is the voltage across the 4 ohm resistor when only 3 ampere current source is acting. So V2 is equal to current flowing through the resistor, that is I3 into 4. So 4 I3 is 4 to the 8 volts. So hence according to the superposition theorem, so the response in this 4 ohm resistor, that is the voltage across this 4 ohm resistor is equal to the sum of the responses of V1 plus V2. Therefore V is equal to V1 plus V2, so 2 plus 8 is 10 volts. So this is the how to apply the superposition theorem to solve the given network problems. Okay. So let us solve one more example. So find I0 in the circuit in figure using superposition theorem. Now see here. So I won't solve this problem. Okay. So I am giving you as an exam homework problem, but I will give you brief idea how to solve this problem. So here we have to find out the I0 by using superposition theorem. So the I0 is the current flowing through the 5 ohm resistor. Okay. So how many sources are there here? See here, 3 sources are there. One is 4 ampere current source, next 20 volt voltage source. So 5 I0 voltage source. So here 3 sources. So this 4 ampere current source and 20 volts voltage source are independent sources, whereas this 5 I0 voltage source is a dependent voltage source. This value is depends upon the current flowing through the 5 ohm resistor. Okay. So, we have to solve this network by using the superposition theorem. See, first I assumed that, see in this first case, I assumed that only 4 ampere current source is acting. Now, the voltage source is replaced with short circuit. See here, the voltage source is replaced with short circuit. Okay, the voltage source replaced with short circuit. Now, find out the current, that is I naught dash. Let us say I naught dash. In the next step, only current voltage source is acting 20 volts. Now, current source is replaced with open circuit. Current source is replaced with open circuit. Now, find out the current in the 5 ohm resistor. Let us say that is I naught double dash. Now, according to the superposition theorem, so the current flowing through the 5 ohm resistor is equal to the I equal to I naught dash plus I naught double dash. That is the superposition theorem. Now, you please solve this homework problem as an example problem. So, this is given to you. Okay. So, next one is the Thevenin's theorem. So, what is the Thevenin's theorem statement? So, Thevenin's theorem states that, so a linear two terminal circuit or network, a linear two terminal network can be converted into a simple equivalent circuit which consisting of only voltage source in series with resistance. This is the superposition theorem statement, where that voltage source having the voltage called V Thevenins, that V Thevenins is nothing but our open circuit voltage across the terminals, and the resistance we are calling as a R Thevenins, or that R Thevenins we are calling as a equivalent resistance seen from this open circuit terminals. So, this is the Thevenin's theorem statement. That means, you take any big network. So, this network consisting of any number of energy sources, inductor, resistors, capacitor, any number of elements, okay, but with open output target terminals, So, this entire network can be converted into the only one single network which consisting of only voltage source, that is V Thevenins called open circuit voltage, and the R Thevenins called the input, that is the equivalent resistance seen from that open circuit terminals. Now, for the AC networks also, okay, any network consisting of any number of sources or elements, so with open output target terminals, so which can be converted into the equivalent circuit, that is called Thevenin equivalent circuit, which consisting of V Thevenins, that is called open circuit voltage, V Thevenins equal to open circuit voltage, and the in series with the Z Thevenins. Okay, that is the impedance seen from the open circuit terminals. So, this is the statement of the superposition theorem. Now, let us solve. So, how to find out this Thevenin's voltage, that is open circuit voltage. So, here V Thevenins is equal to VOC, that means open circuit voltage. Let us see here linear two terminal circuit is there. So, let us see linear two terminal circuit is there. So, whatever this linear two terminal circuit, so that A, B, so two terminals are there, A, B terminals. So, we have to find out what is the voltage across that open circuit terminals, VOC. OC means open circuit terminals. Okay. So, this we have to find out the Thevenin's voltage. So, next one is how to find the Thevenin's resistance, that is R Thevenins equal to R input. See here, network R input is nothing but the resistance seen from that open circuit terminals only. Okay. So, when you are finding this resistance, okay, so we have to turn off all independent sources. We have to turn off all independent sources. How to turn off all independent sources? In the same as the superposition theorem. So, replace the voltage source with short circuit and current source with open circuit. So, this is the steps to follow when we are applying the superposition Thevenin's theorem for the given network. Okay. So, there are some 3 different cases how to apply the superposition theorem. The first case, the case one is, if the network given network has no independent sources, no dependent sources. That means, if the given network has only independent sources, then how to proceed to apply this Thevenin's theorem. So, first of all, if the network has only independent sources, that is, if the network has no dependent sources, so turn off all independent sources. Turn off all independent sources. Turn off means what? You have to kill the sources. Voltage source replaced by short circuit and current source replaced by open circuit. So, therefore, R Thevenins can be obtained by simply parallel series combinations, you know, when two resistors R1 R2 connected in series, R1 or R1 plus R2 equivalent resistance, and in the two resistors R1 R2 connected in parallel. So, the equivalent resistance is R1 into R2 by R1 plus R2. So, series connection means R1 plus R2. In the same manner, you apply the techniques, you can easily find out the R Thevenins. Okay. So, this is the first case. Okay. So, let us solve one problem on this Thevenin's theorem. Okay. So, here find the Thevenin equivalent circuit of the circuit shown in figure to the left of the terminal, that is AB. See, here AB is given. So, across these terminals, so AB, we have to find out the Thevenin equivalent circuit, which consisting of only one voltage source, that is Thevenin's voltage called open circuit voltage, and Thevenin resistance called equivalent resistance seen from the terminals. Then find the current through the RL, that is a load current RL, when RL is equal to 6 ohms and 16 ohms and 36 ohms. That means, when you changing the loads, okay, what is the current? See here, RL is equal to 6 ohms. So, that means you replace this load resistance and we can easily solve the current once you obtain the Thevenin equivalent circuit for the given network. So, that is the importance of the Thevenin's theorem. Now, see here, if it is if you apply any other nodal analysis, mesh analysis method or any other methods. So, if the resistance value changes, the load resistance RL value, then you have to solve for different resistance. But this Thevenin's theorem, if you solve once, then whatever the changing of this load resistance, you can easily solve the what is the current flowing in that resistance, load resistance. Okay. So, this is the beauty of the Thevenin's theorem. Now, here first to find the R Thevenins. So, how to find out the R Thevenins? So, just now I told you. So, first one voltage source, 32 voltage source is short circuit. So, 2 ampere current source open circuit. So, you remove the disconnect the RL. Okay, you have to disconnect the RL, because we have to find out the open circuit voltage across that AB terminals. Okay. So, this is what the first network is give the. So, we have disconnected the RL. So, this is what we have to find out the R Thevenins across these terminals. Next to current source replaced to open circuit, voltage source short circuit. Now, what is how to approach this R Thevenins? So, here 4 ohm resistor and the 12 ohm resistor, okay, in parallel. So, therefore, and the combination will give you the 1 ohm is a series. Therefore, 4 is parallel with 12 here, see here. So, 4 is parallel with 12 and plus 1. Therefore, 4 into 12 by 4 plus 12 is 16 plus 1, then you will get 4 ohms. Now, how to find out the open circuit voltage? How to find out the open circuit voltage? So, to find out the open circuit voltage for this network, okay. So, whatever the technique you want to use, you can use. See, you are using here mesh analysis. So, let us see current flowing in the first mesh is I1 amperes, okay, and the current flowing in second mesh is I2 amperes. Okay. So, find the Thevenin. So, first we have mesh analysis. See here, now apply the KVL Kirchhoff voltage law in this first mesh. So, minus 32 plus 4 into I1 plus 12 into I1 minus I2 equal to 0, that is the equation 1. See here. So, minus 32 4 into I1 plus 12 into I1 minus I2 equal to 0. Next to what is I2? So, I2 is given. See here, I2 directly we know that I2 is equal to minus 2 amperes. I2 is going clockwise direction, but 2 ampere current source is coming towards up. Therefore, I2 is equal to minus 2 ampere directly. So, substitute this minus 2 amperes in minus 2 amperes in this equation, then you will get the I1 is 0.5 amperes. So, once you get the I1 and I2, so it is easy to find out the voltage across this Thevenins. See here. So, therefore, Thevenins is equal to, that means voltage across the 12 into I1 minus I2, okay, 12 into I1, that means whatever the voltage across this 12 ohm resistor, okay, in this circuit, whatever the voltage across this 12 ohm resistor, same voltage will be appear for the 2 ampere current source. Therefore, same voltage will get appear across the open circuit terminal, because as this open circuit the current flowing to the 1 ohm resistor is 0. So, therefore, we have to apply the, we have to find out the current voltage across the 12 ohm resistor, that is 12 into the currents are I1 is entering and I2 is leaving, I1 minus I2. Therefore, 12 into 0.5 plus 2.0, that is equal to 30 volts. So, Thevenin's voltage is 30 volts. So, there are different techniques to solve this. So, you can apply the nodal analysis, mesh analysis. So, it is easy to find out the Thevenin's theorem, okay, Thevenin's voltage. So, therefore, Thevenin's voltage is equal to 30 volts. Now, therefore, see here in this step you are applied the nodal analysis method. So, 32 minus Thevenins by 4 plus 2 is equal to Thevenins by 12. So, you please cross multiply that, then you will get the Thevenins 30 volts. So, whatever the principal technique you want to solve whether it is a mesh analysis, node analysis or current division, voltage division principle, basics, Kirchhoff's law, current laws, Ohm's laws, but it is easy to find out the voltage. So for this circuit is the Thevenin's equivalent circuit for the given network. See, so whatever this circuit is there, so this is the given circuit. What is the given circuit? This is the given circuit. So this given circuit is replaced by, entire circuit is replaced by only one voltage source and one resistance in series with it. See that. So this is what the, so this is what, see, Thevenin's voltage is 30 volts, that is open circuit voltage. Thevenin's resistance is 4 ohms, that is a input resistance seen from the terminals. So this is the Thevenin equivalent circuit, and we have to connect the whatever the resistor we are removed, that is the load resistance RL, and you reconnect it. Now you have to find out the current in the load resistance when now tell me from this what is IL is equal to? IL is equal to P by R, that is V is 30 by 4 plus RL. Okay. So V Thevenins by R Thevenins plus RL, therefore 30 by 4 plus RL. Okay. Now when RL is equal to 6 ohms, then what is IL? So 30 by 10, 4 plus 6 is 10, so 3 amperes. If RL, that is, if you are changing the loads, that is, you are changing the loads. So turn on fan, turn offing other appliances. Okay. So when the load is changing, what is the current run by the circuit? 3 amperes when the load is RL is 3 amperes, when the RL is equal to 16 ohms, 1.5 amperes, that is load is decreasing here. Resistance is adding, load is decreasing. RL is equal to 36 means, so 0.75 amperes. When the load is increasing, so current also changes. That is what the how to apply this superposition theorem and Thevenin's theorem for the given network. Okay. So let us summarize this today's lecture. That is, so to apply the superposition principle, there must be at least 2 sources should be present. Okay. There must be 2 independent sources must be present. Next, superposition theorem is not applicable for calculating the power. Thevenin's theorem and superposition theorems can be applied to only linear networks only. So the limitation of the superposition Thevenin's theorem is which is not applicable for the non-linear networks. So this is the concept of the, that is the superposition theorem and Thevenin's theorem. So this is the summary of the today's lecture. So superposition theorem statement is clear, that is the response in any linear network, okay, the response in any element in a linear network is equal to the algebraic sum of the individual responses. Now Thevenin's theorem, in any linear network with open output target terminals can be converted into the equivalent circuit which consisting of only one voltage source called V Thevenins, that is open circuit voltage, and in series with the resistance or impedance, that is R Thevenins or Z Thevenins, that is the equivalent resistance or impedance seen from the same open circuit terminals. So this is the today's lecture on superposition theorem and Thevenin's theorem. Okay, we will join in the next class. Thank you.